So this is the pattern of a cyber-physical system of interest. For the inverted pendulum case, we're missing the network fabric and we're missing the multiplicity of controllers. That's going to come into later assignments when we'll start to play with that. Okay. But for the moment, we're just going to get one little very simple feedback loop where there's an interaction with a physical point. And so the real things that we want to focus on is reliability, repeatability, and testability of the system. So I want to start today by giving you some perspective on how this is typically done today in some of the more cutting edge work, right? Not that sort of old-fashioned embedded software stuff, but people who are doing, integrating machine learning, computer vision, and so forth into their cyber-physical systems, right? The kind of techniques that they use are, frameworks like ROS, the Robot Operating System, which is pretty widely used in research circles and is starting to get used in industrial settings, but it has potentially some problems. MQTT is very widely used in Internet of Things applications. So it's a publish and subscribe framework for connecting thermostats and all kinds of other devices to the internet. Actors, which are quite heavily used in a lot of cloud computing IT applications, are also starting to get used in some embedded applications. Service-oriented architectures, I'll talk about a little bit. Shared memory architectures are not so much in favor these days. They tend to be rather difficult to make work. Yeah.
You mentioned that ROS publish the messages. You have the recording for the timing. Do all MQTT workgroups do the same thing as ROS, or it's just about ROS?
MQTT also does not have any timing semantics built into it. But it's not just a timing issue, it's also an ordering issue. Okay, the issue is that if you have two agents that are publishing to a topic, there's no way to control semantically the order in which those published events occur. It ends up being an accident of your implementation, which one will get published first, for example. That's one scenario that arises. Similarly, if you have an agent that's subscribing to two topics, irrespective of the order in which the publishings occurred on those topics, that order may not match the order in which the agent handles the incoming messages. Okay, and let me zero in on that because I'll show you a very concrete problem. So just to make sure we're all on the same page, what is publish and subscribe? Well, components publish events on topics, and the topic is just a string, it's a name. Okay, and there's some sort of a broker infrastructure that may be centralized or may be decentralized that keeps track of which components are publishing which topics and which components are subscribed to each topic. And whenever a component publishes to a topic, it's up to this broker to distribute the published data to all of the subscribers. Okay, it's a fairly straightforward, conceptually straightforward thing. Now, a component can subscribe to multiple topics, and it has a callback function that it specifies to the broker, perhaps, or yeah, that's typically how it will work. And so the way that it gets notified of a subscription event is that its callback function gets invoked. Okay, but you have to keep in mind that when a callback function, whenever a function gets invoked, if you're writing a program on a single computer and you're completely in control of when the functions get invoked, then you can understand pretty well in what order things are going to happen. But as soon as you're in a concurrent situation where there's external events that can cause a function invocation, there's quite a few things you need to worry about. One, does the function invocation preempt some function that you might already be executing? You might be executing a previous notification function. A new notification comes in. Does this new notification preempt the old one? In ROS and MQTT, by default, there's no preemption. So the messages are invoked in a mutually exclusive way. But the order is not defined. Okay, so it's an accident of, it's a race condition, right? Whichever message comes in first will typically result in that method being handled first. Okay, make sense? ROS2 is a fairly sophisticated system. It uses a pub/sub infrastructure, and it's built on top of this networking service called the Data Distribution Service. And DDS is a pretty nice service. It has a lot of features in it for getting some real-time behavior. So you can assign priorities, for example, to certain messages. And that can help you to control the order in which things occur. But it's not, priorities in this case are not really a semantic property. So they bias the implementation, but it's a bias, it's not a correctness specification. So the net effect is that when you use DDS with priorities, you may make anomalous behavior very rare, but you can't really eliminate it. Okay. And my claim is that making anomalous behavior rare is sometimes worse than making it common, because if it's common, you will detect it in testing. If it's rare, you may not detect it in testing. You might ship the product and detect the existence of this anomalous behavior only after your product is in the field. And that's a bad situation, especially in safety critical systems. Okay. So making anomalous behavior rare is not really a good goal in cyber-physical system design. I mean, of course, up to a point, right? Anomalous behavior cannot be eliminated completely in any physical realization of a system. Any physical realization of a system can fail in unexpected ways. That's just a fact, right? But you don't want it to fail in expected ways. Okay, so your goal is always to reduce the possibility of these expected failures. All right, so there's a very nice project that was done by Sarush Pateni, who's a PhD candidate who just finished his thesis, in fact, at UT Dallas, and I've hired him as a postdoc to work in my group. But he took an open source piece of software called Autoware.auto, which is pretty widely used in the self-driving car community as kind of a starting point for research. It's a framework, a ROS-based framework that has been deployed on physical cars. You can download a version of it that runs completely in simulation using an automotive simulator called LGSVL, which comes originally from LG, the Korean company, okay? But it's a very nice automotive simulator that's pretty realistic about the behavior of the car, and is actually used by a lot of car companies. This is an image from the LGSVL simulator, as is this. You get these kind of different views, map view and personal view, and it also includes models of the dynamics of the car, so that you get reasonably realistic responses to application of the brake and things like that. Okay, it's mostly built in C++, a bit of Python in there mixed in, but mostly C++. And it uses ROS for all these components to interact with one another. So this is a picture. This picture is generated from the ROS architecture specification. So there's a ROS tool that generates pictures like this that shows you what the ROS components are. And each of the arrows is a publish and subscribe topic. Okay, so these are in ROS, there's a name associated with this. And notice an interesting phenomenon about this architecture is that most of the topics are actually doing point-to-point communication. There's a single source and a single destination. Which is not really what publish and subscribe shines at. That's not really what it was intended for. Okay, but that is largely what it's been used for. So Soroush did a study of this where he looked at a particular aspect of the behavior and ran the simulation in an automated way a very large number of times, 300,000 times. Okay, and he looked at a particular sequence, a particular interaction within the system between the simulation of the car and the behavioral planner. And in particular, there are two topics that are used for the car to communicate with the behavioral planner. One of these topics is a report on any change of state in the car. So in particular, if the car is in drive and switches to reverse, an event will be published on that channel saying, I'm now in reverse. Okay, it's a notification of the change of state of the car. The kinematic state is a sequence of notifications about the velocity of the car and various other kinematic behaviors. So he looked at this and looked at a particular sequence where you had an event that put the car in forward, an event that produced a positive velocity on the kinematic state, an event that then switched the car into reverse, and an event that notified of a negative velocity. And then looked at the order in which these events arrived at the receiving end. And the vast majority of the time, they arrived in exactly this order in which they were produced. Okay? Almost all the time. But every once in a while, they would arrive out of order. And in particular, the behavioral planner will see that the car is in forward gear and that its velocity is negative. Okay? Now the question is, what should the software do in the behavioral planner when it gets a notification like that? Okay. Car is in forward and it's going backwards. What do you think it should do? Just ignore it and assume it's an anomaly? Should it assume that there's been a crash? And that the car is in serious trouble? Should it assume that there's been a mechanical malfunction? Switch to a safety scenario? What should it do? It's hard to know, right? The reality is that that particular ordering can arise just because you're using thumbs up. And so you don't really know. I mean, if you ignore it, then you've built a system that fails to handle a true anomalous condition that could be dangerous. So just ignoring it is probably not a good answer, but I can come up with a better one because you can't know what the source of the reason for the lack of ordering here. Okay, there's no semantics to the ordering, so there's no correctness criterion that you can apply in this case. It's a fundamental problem with PubSub. So he ran 300,000 tests, found that these errors were really quite rare. In fact, so rare that, I mean, you probably wouldn't run it 300,000 times, certainly not in a real video. Okay? That's hugely expensive. You'd be out there for months doing those tests before you see the anomalies. So they're really not very likely to show up in testing. But once you ship it and put it into 500,000 cars, it is going to show up, right? Guaranteed. Let's look at service-oriented architectures. So what do we mean by a service in this case? Well, service is a pretty broad term, but a pretty common definition for a service-oriented architecture is where a service is a procedure that is exposed by a component that can be called remotely. So some external device can invoke that procedure. And but you could do this in a way that the caller waits for the results. It's called a synchronous invocation of the service. Or you could do it in a way where when you call the service, you get back what people call a future, which is just a handle to the result. And then you keep doing some computing until you actually need the result. And then you block until you actually get the result using that future. Okay, so that's an asynchronous call. Typically, service invocations are mutually exclusive. So if you have a single service and two different clients invoke a service by trying to invoke a procedure, the two procedures will not execute at the same time. One will run to completion and then the other one will start. Okay, so it's a mutually exclusive invocation. But just like publish and subscribe, there's no semantics to the order in which these procedures get invoked. So you again have a race condition where the order is determined by the accidents of your networking latencies or your execution times or whatever. Okay. So there was another study done by another one of the participants in the Lingua Franca project, Christian Menard. So Christian Menard is a PhD student at the Technical University of Dresden in Germany. And he looked at AutoSAR, adaptive AutoSAR in particular, which is a relatively recent variant of AutoSAR, and an implementation that uses this network fabric called SumIP. And he took a demo program that comes with the download. When you download, it's a reference program. Okay, this is how you use AutoSAR. He ran that demo program quite a few times and found the same kind of problems that Sarouche found. Okay, and the particular problem that he was addressing was an emergency brake assistant. That was the demo program. So this emergency brake assistant had a video provider, a video adapter, where we get frames of video, some pre-processing, a computer vision algorithm, and then the emergency brake assistant that would apply to braking. All right. And he found a variety of different kinds of problems. The input mismatches, I thought, were the most interesting ones, where you essentially were getting contradictory information from the system because of the way, the order in which the services were being invoked. Let's look at actors, okay, which is another strategy. So we've looked at two strategies so far: publish and subscribe, which is used in ROS; service-oriented architectures, which are these remote procedure calls. Actors is a third thing, and it has a long history. The actor model was first introduced by Carl Hewitt way back in the 1970s. It was further developed by Hewitt's PhD student, Gu Laga, who then became a professor at Illinois and it was Gould who actually really developed the formalism and developed the concept of actors. But loosely, actors are message passing devices where there's no centralized broker anymore. So unlike publish and subscribe, an actor has a reference to another actor and sends it a message. And the semantics of actors is that the sending of a message is send and forget. Okay, so you just send a message and then go on doing what you're doing. You don't wait for a response. You don't even make any assumption that the recipient has seen that before you continue. Okay. So what happens at the receiving end is that messages come in and they get queued up. They get queued up if the recipient actor is busy processing a previous message, right? Otherwise, they just get processed right away. But if you get more than one message coming in, they'll queue up, and then the handlers for each type of message will be invoked, again, in a mutually exclusive way. Right? So kind of similar architecture, but once again, there's no semantics to the ordering in which these messages are delivered. If they're originating, if these messages coming along this type, this channel are originating from one actor, and these messages are originating from another, there's no meaning to the order in which they arrive. And the order can be determined by the accidents of execution time, the accidents of message delivery, etc. All right. So let's look at a very specific example. All right. So we're gonna look at some code, and this is only slightly abstracted from the way you would write these factors in Akka, which is a Java-based factor framework that's pretty popular out there. The Java code will look a lot like this, but it's just a little bit pseudocoding so that we don't get bogged down in details. So we have this actor foo that has a local state variable, okay, which is an integer that gets initialized to 1. And it can receive 2 types of messages, a double message and an increment message. When it receives a double message, it invokes this handler, which doubles the value of the state. And when it receives an increment message, it invokes this handler, which increments the value of the state by the message payload, and then prints the state. Okay, so we see some results when you get one of these increment messages. Okay, so everyone understand how this actor works? It's pretty straightforward, right? Okay. So let's make an actor that sends it some messages. So how does this work? Well, in Akka and many of the actor frameworks, you create a main handler. You can create a main handler in an actor. And this is just something that gets invoked right away from the beginning. You can think of it as there's a message type main that always arrives when you start up the program. Okay. So this handler gets invoked. And the way that this actor framework works is that it'll actually create an instance of the actor that it wants to send messages to. So it invokes a constructor of the actor foo that we just saw, and then sends in 2 messages, bubble and increment. Okay? Pretty straightforward. So now let's put these together. What will be printed? 3, right? Under what assumptions? What are the assumptions you have to make to conclude that 3 will be printed? Suppose that these are running on 2 different machines. Okay. What assumptions do you need to conclude that 3 will be printed? Yes.
The order must be exactly as the order is here.
Right. So the messages have to be delivered reliably and in order. Right? So that's actually not hard to achieve with today's technology, right? We have a very nice technology, internet technology called TCP/IP that does exactly that. When you open a socket connection using TCP/IP, you are guaranteed that any message you send will be received eventually, okay? Barring some catastrophic failure of the hardware, of course, because that's always a possibility, but it'll be received eventually. And if you send 2 messages in some order, they will be received in the same order that they were sent. Okay? That is guaranteed even in the presence of packets dropped in the network. Suppose the first message you send gets lost. Okay? TCP/IP the receiving end might receive the second message, but it'll say, wait a minute, I'm not ready for this message. Okay, it's built into TCP/IP. There's a missing message here. All right, so it's not going to forward that, it's just going to queue it up. All right, and it's not going to send an acknowledgement. And when a sender fails to get an acknowledgement, it retransmits the message. So even if the first message got dropped, it will get retransmitted, and it will be received eventually in the right order, which it was sent. Okay. So you can get perfectly repeatable behavior with a system like this with very high reliability using TCP/IP as the connection fabric between these 2 components. Of course, if you're executing them on the same platform, then you still have to take some precautions if you're executing in two different threads. For example, you got to make sure that you do things in such a way that things will happen in the same order. But it's not that hard to do. Okay? But let's complicate the program only slightly. Suppose we add a third actor, okay, that has a handler called pass. So when it receives a message pass, and pass will have as an argument an actor. This is one of the things that the actor community is very proud of. They love the fact that you can send actors as messages. So this receives an actor as a message, and then it invokes, it sends that actor a message. No. So it's really just forwarding double. Now, let's combine these three actors. So now I've changed the main handler. So it creates an instance of foo, then it creates an instance of this intermediate actor. It's going to do a relay. It sends a message to the relay, and it sends a message to the foo that it created. Okay? Sends an increment message to that guy, a pass message to this guy. Now what is printed? This is, by the way, about as close as you can get to a no-op, right? A no operation in actors, right? All it's doing is forwarding a message. So you'd think it should print 3 again. But again, what are the assumptions that would be needed? And in particular, is TCP enough? What do you think? Yes.
Yeah, now kind of separate queues. One might be delayed and parallel, and they're not related anymore.
Yeah, they're not. You know, if you have a TCP connection from here to here, a TCP connection from here to here, and a TCP connection from here to here, each of those connections is guaranteed to deliver messages in order. But that does not provide any guarantee about the order in which this guy receives the 2 input streams. In fact, if you were to implement this in Akka, almost certainly the order will be reversed, right? Because this guy will take a little longer. There's 2 message hops, right? So even though you sent the double message first, probably it's going to get delayed here and be received second by this guy, which means that what will be printed will be what? 2, not 3. Right? Because the state starts as 1, you get this message first, you increment it by 1, you print 2. Then you get the double message, and now the state is 4. Okay? Your error now is persistent. Because the state of this actor has changed in an undeterministic way. So that means this is not a transitory phenomenon. Right? The persistent state, the ending state of this actor can depend on the accidents of message delivery. Okay, so you get a persistent form of non-determinism here that could be quite seriously problematic. Now, you remember the aircraft door example that I showed the last time, right? Where you wanted to disarm the door, right? If you have an aircraft door using just 2 actors and you use TCP/IP, fine, no problem, it's going to work well. As soon as you put this vision system in between, you're in trouble, right? Because now you're not going to have any guarantees about the order in which messages are going to be delivered to the destination. Right? Does everybody understand what the problems are here? So, so the fact is that the messages are handled in non-deterministic order, and this is the problem. Oh, so what could we do? Well, you know, one thing we might try to do is, you know, put some constraints on the execution of this system by doing some analysis of what we think it should do. Okay? So a reasonable thing might be a dependence analysis, right? We see that this guy is sending a message to this guy, which is forwarding it to this guy. So maybe we should impose some constraints to make sure that this guy is able to finish and complete before this guy is allowed to do anything. But the problem here is that in this actor framework, there is no place in this program where you know what the dependencies are. This is a distributed program, for example. The machine running this doesn't know what the dependencies are. The machine running this doesn't know what the dependencies are. The machine running this doesn't know what the dependencies are. This information is all local and it's controlled by low-level code. This actor is creating an actor and sending an actor to this guy. Doesn't know what this guy's going to do with that actor. Okay. What it does is under program control. What if it has a conditional in there and it doesn't always forward the message? In that case, you don't want this guy to sit there and wait for a message because you'll fail to open the door when you should have opened the door, or you'll fail to disarm when you should have disarmed. Right? And the point is here that there's no place in the program where you know what the dependencies are. And in fact, in order to even figure out what the dependencies are, you're going to have to analyze low-level code. What is this condition? Suppose it calls some complicated function. And now you want to delay this if that complicated function returns true and not delay it if it returns false. It's going to be a very difficult kind of analysis to do. Right? And if you're writing an actor framework using this kind of strategy, it's up to you as the designer to figure out what kinds of scenarios like this could arise and how to solve them. And they're really not easy to solve. These kinds of problems, even with such simple programs, are really, really difficult to solve. So returning to this concrete example, how could we solve it? Right? This is a very simple example. So let me show you how we solve this in Lingua Franca. So we're going to do a little coding exercise here. All right. I will create a brand new file. Let's call it junk.lf so that I know to delete it later. Oh, that's strange. It says I'm screen sharing. Okay. Now you can see it, right? It says no main reactor screaming at us. All right, let's do this in C. And let's see, the first reactor, oh, shoot. I think every time I go get out of PowerPoint show mode so that it stops trying to switch. Okay, so let's create the foo actor first. It's got two message handlers, one that doubles and one that increments its state. All right. So in Lingua Franca, the way we do this is we create a reactor named foo. It has an input double, which is just a Boolean, right? And an input increment, which is an integer. And it has a state variable, let's call it S of type int, that is initialized to 1. And then we have a reaction to the double input. Can you see this in the back of the room? Okay. We have a reaction to the double input, and now Lingua Franca has this funny syntax where it has these this delimiter, curly brace equals, and this separates the Lingua Franca code from the target language code. So what goes in between the delimiters here needs to be C code. It has to be valid C code because the target is C. If you choose the Python target, what will need to go in here will have to be valid Python code. If you choose the Rust target, it will have to be valid Rust code, etc. Okay. In addition to it being valid C code, there's an interface in the C code. You can get access, for example, to the state variable and to the input values. Okay, so in particular, the double, let's say we don't even care whether it's true or false. We're going to double anytime we receive an input there. All right, that would be one possible design. Then we don't have to do any testing because this reaction will be invoked only when there's a double input. And the way you reference a state is that the state is on a struct in C that's called self. So to double it, all I have to do is multiply it by 2. And that'll take care of it. And then I can declare a reaction to the increment input that increments the state. And the increment input is, the value of the input is accessed like this. Okay, the input itself is also a struct in C, and the value is one of the fields. There's another value, there's another field like, there's a Boolean field called isPresent. You can use to check to see if whether there's actually an input, but in this case, we know there's an input because there's only one trigger to this reaction. And so it'll only be invoked if the input is present. So I can do that, and then I can print the result. So in C, you do this like this, printf, and we'll print the state variable. And there we have this reactor foo. Okay. Let's build the rest of it. So we'll build the pass-through reactor. Which has an input, let's just call it in, no, it's, I guess on the slide it's called pass. So we'll call it pass. And an output, let's call it double, because that's what it's forwarding. It's a Boolean. And it has in reaction to pass, we declare an effect that it could produce a double output. And then we invoke a built-in function to set the output to whatever the value of the input is, like so. Okay, so now we got a second actor. And now let's take a shortcut and just directly produce an instance of foo. Let me give myself a little more room here. I connect the double output of P to the double input of F, like so. And then let's just create a reaction so that at startup, this is like the main in, whoops, I need the delimiters. This is a reaction that will be invoked when the program gets started. And let's see, what is it that we want to do there? We want to send a message to the pass input and a message to increment. So we say, oh, we're going to have to declare these as effects. So F dot double. No, we're sending to F the increment, and we're sending to P we pass. So these are two effects that can happen. So I can say LF set. Let's do this in the same order. Pass. So pass. True. And set to f.inc a 1. There we have a complete Lingua Franca program. Okay. I can compile this program by clicking on this little gear icon. This is I'm using Epoch, which is one of the 2 IDEs that are available to you. The other one is Visual Studio Code. You can monitor the effect of the compile in this console window. My version of Epoch here is a few days old, and there's these deprecation warnings that have been gotten rid of. So I think they're gone. So unless you downloaded it before they got removed, but if you get deprecation warnings, it's no big deal. Right, the code compiled correctly despite the warnings. And then I just want to show you what happens here. This is the directory in which I think, where did I put this? Junk is, it happens to be in the Furuta pendulum folder. Yeah, so there's my junk program. Okay, the way that a project in Lingua Franca is structured, at the project root, you have a source directory, and anything you put within that at any level of hierarchy will be part of your project. Okay, and then when you compile the program, it automatically puts an executable into the bin directory. So we can look at the details in the bin directory. And you'll see that junk was updated at 15:01 on May 4th, which is more or less now. And you can run it. It gives you the value 3. And no matter how many times you run it, it will always give you the value 3. Now you might say, well, that's cheating because it's all executing on the same CPU, right? But I can actually just change this to a federated program. And, whoops, push the wrong button. And now there should be, whoops, now I actually got an error. What is the error? Oh, yeah. Actually, this architecture that I just created is not permitted in the federated version. The reason is that in the federated version at the top level, every reactor that's contained by the top level generates to a separate program, and it doesn't know what to do with this reaction. Okay, so let's fix that. So we can build the architecture more like what it's done here, create an actor bar for that program. So let's say reactor bar as an output pass of type bool, and an output that's what we want. Type pass and increment, yeah, of type int. And then it's going to have this reaction. Except that now this is just that. So now I have to create an instance of it. Connect it up. Got a thunderstorm? Nice. We don't get thunderstorms in California. We actually don't. People who haven't been there are surprised by that, but they just don't happen. Yes, we have all kinds of other problems. Yeah. Okay, so this should now compile as a federated program. All right, I hope. Yeah, we got our deprecated warnings, but everything worked okay. And now, if I look at what's in bin, there's a bunch of programs. Okay. This one labeled junk is actually a script that launches all the other programs, but you don't have to launch them that way. You could, in fact, ship these off to another machine. In fact, you could even do that within your source code. You can say that you want food to be at, we have a machine at Berkeley, wessel.eecs.berkeley.edu. And if I have the appropriate permissions, it'll actually ship the executable to that machine. And the script that it generates will invoke it on that machine, and it'll interact with this rest of this program. But I'm not going to try to do that in demo mode here because all kinds of stuff can go wrong, right? But instead, what I'm going to do is show you this script. So if I do if I look at the script, it's pretty short. It's just a bash script, right? It has some functions to kill off any dangling processes that might be there, and then it eventually launches the program. And I'm hoping if I run it, it'll actually launch all these programs and print 3. There it is. Okay. And it'll print 3 every time. So, okay. So let me explain why this is different from the 3 mechanisms that we looked at. This is not the actors of Hewitt and Gulaga. This is not publish and subscribe. And it's not service-oriented architecture. So it's something else. Okay. We call the model of computation reactors. The difference, there are 3 core differences. My machine is not responding. The first is this use of ports, okay? Explicit inputs and outputs. And instead of an actor referring directly to another actor or referring to a topic, it only refers to its own ports or possibly the ports of a contained reactor. Okay. Why does that help? Well, the reason that that helps is that now there are places in the code where the dependencies are evident, because there's a nice hierarchy here. And at any point in the hierarchy, the component that contains all these other reactors knows what their interconnections are. And it can use that information. When it generates the code to execute in multiple processes here, it uses that information to generate the appropriate regulators for the execution of that code to ensure that those dependencies are respected. And in this particular topology, right, where this is kind of annoying, you have to get out of presentation mode to show another window. But okay, just to emphasize what's going on. When these 3 components are running as separate programs, they run as completely separate programs, right? It started out with separate processes, The code that's generated imposes constraints on their execution that guarantees that this guy, if this guy is going to send in a message, that it will see that message before it sees this message. Okay, why before? Well, if I look at the structure of this has two reactions, and they were given in a particular order. Okay? The double reaction was given first, and the increment reaction was given second. And that means that if there are two logically simultaneous messages, these are treated as logically simultaneous, okay? Not physically simultaneous, because there is no such thing as physically simultaneous. They're logically simultaneous, right? If there are ever going to be two logically simultaneous messages, this one will always be handled before this one. Right? Yes.
So the ordering is right from the occurrence in the code. So.
That's right.
Okay.
Within a reactor, all reaction invocations are mutually exclusive, as they are in all these other frameworks. But in addition, there's this constraint that they will be invoked in the order of declaration whenever they are logically simultaneously enabled.
Okay. So it's important to know the order. So
yeah,
I want the mental reaction first, and then first, so specify.
So let's change the order. Okay. Diagram gets redrawn. What do you think we're going to see printed? Four? We're going to see two, right? Because the printing is getting done in this guy. All right, so let's just verify that. Two. Okay. And that will be very reliable. Okay. You can do it. Yes. Okay. So this use of ports is kind of an important part of this, right? It gives you a nice separation. It also sort of makes these components a little more modular. The actor people are really proud of the fact that they can create actors and pass them messages, and then under arbitrary program control, do stuff with them or not do stuff with them. But there's a price for that generality, which is that you lose the ability to have anywhere in the program any understanding of the relationship between your components. Okay. So the second part is hierarchy, which is a really important part of this, because this top level guy is a reactor. It could have its own ports, actually, and you could embed it within another reactor. But the point is that within each reactor, which possibly contains other reactors, all the dependencies are known to this reactor. This reactor doesn't know what these dependencies are, right? But this one does, yes.
Can these reactors be organized in libraries and be reused?
They can be put in libraries and reused, yes. Absolutely. Yes.
How is it different from deploying the PDS to priority?
The difference is that priorities are best effort thing, right? They tell the network, if you have competing messages competing for the network, prioritize this one over that one. Okay, but the problem is that the race condition might not be occurring at the networking level. It could be occurring because of execution time delays in your program. Okay, and so you still have no semantic ordering. Part three of the solution is scheduling, which is really all about imposing some constraints on the order in which things happen. And that ability to do that scheduling is enabled by being able to have a view of these dependencies. Okay, so in particular, in this particular case, this guy generates two events. They're logically simultaneous events. Okay? And we'll talk a bit about that next Monday. We're going to go into the temporal model in Lingua Franca in some detail, but for now, just think logically simultaneous. Moreover, when this guy processes the event, its output is logically simultaneous with its input. So logically, this executes instantaneously. Physically, of course, not. But logically, it executes instantaneously, and consequently, its output is still logically simultaneous with this. And because these two are logically simultaneous, they will be presented to this reactor at the same time. And the reactions to them will be in the order that they're. Okay. So that's the scheduling part of the equation. Scheduling becomes especially interesting because if this guy were to choose not to produce the event, that doesn't create any problems at all. The absence of the event is known and is logically simultaneous with the presence of this event. And consequently, this reaction can be safely invoked without invoking this one, if there is no event here. If this guy chooses not to produce an event. All right. So I just wanted to tell you a little bit about this project because, as I said, you guys are guinea pigs, right? You're really kind of the first outside users of this code. These are the people who have been working on it. We've been probably the two biggest pieces of activity are Berkeley and Dresden, but Kiel University has contributed what is in some ways the most important part of this, which is the graphical visualization that you saw getting constructed as I was building the program. That's all the work of these guys at Kiel. There's a few other places. Seoul has gotten much more active recently. It makes it very difficult to do conference calls, as there's no time of day that works. Anyway, these are what GitHub says are the top contributors in the last few months. Notice I'm number 2. I'm a very hands-on guy. I contribute a lot to this repo. This has been the trajectory of commits. See, the project is a little more than 2 years old. Right? It started out kind of slowly with a small team, but it's been growing. And if you get interested and want to contribute, there's a lot of interesting work to be done still. Tremendous amount. So I encourage you, I have arm twisted a few of these people to monitor this Slack channel that we created just for you guys. So it's going to be kind of quiet unless you guys make it lively, right? But so, please use it because we have this team around the world, you should be able to get responses pretty quickly at any time of day or night. Yeah, okay, so these are the issues. Okay, so any questions about this? Comments, thoughts? Yes.
Is it anywhere near doing the Lingua Franca stuff on hardware?
Oh, very good question. Yes, one of the reasons that we have put a lot of effort into the C target is that we want to be able to produce very low level code. Okay. And we have existence proofs where we've run Lingua Franca programs on bare iron machines that have no operating system. And in fact, we're signed up to fully support a board that's been used for an embedded systems class at Berkeley in the fall semester. And we're going to switch over that class to using Lingua Franca to program that board without an operating system. There's also a project that is starting in Norway, but the guy in Norway is going to come to Berkeley in July and work with us for about 6 months to do hardware synthesis from Lingua Franca, so to FPGAs.
Yeah. Are there any targeted architectures that you want to start with? Or
so the existence proofs that we have, we've put Lingua Franca programs onto a research platform that's pretty popular that came out of Denmark called Patmos. It's a multi-core network processor. We've put it on a Nordic Semiconductor 32-bit microcontroller. We've put it on a rather specialized hard real-time machine called a prep machine, which has very rigorous timing behaviors that can be used to control timing of the software down to nanosecond kind of scales. Those are the three platforms that we've so far focused on. There was also a project that mapped Lingua Franca programs onto Arduino, which has its own little programming ecosystem. It's a little bit different, but they showed that it was possible to do that as well. Yes.
Is it possible to define a reactor a deadline for a message?
It,
That if I don't receive a message in a certain amount of time, that another reaction or whatever is triggered?
yes, I'm going to talk about deadlines on Monday because we're going to talk all about timing on Monday. It turns out that deadlines are a pretty nuanced issue. I didn't realize that it's not a very simple concept, actually. But we'll talk about that on Monday. So, what I'd like to do for the rest of today is a little bit different. Remember, I told you the last time that I wanted each class, we have a 2-hour time segment, and you can't